plug and play regularization using linear denisers. Plug and play regularization, what we are using? Which linear deniser using? In plug and play regularization, the knowledge of the forward model is combined with powerful denoiser to obtain state-of-the-art image reconstructions. In plug and play regularization, the knowledge of the forward model, the knowledge of the forward models combined with denoisers. Forward model knowledge combined with linear denoisers for image reconstructions. This is typically done by taking a proximal algorithm such as FISTA or ADMF. This is the proximal algorithm. And formally replacing the proximal map associated with a regularizer by non-local means PM3D or a CNN denizer. That is PM3D or a CNN denisers using which algorithm? Proximal algorithm. Proximal algorithm for plug and play. Proximal algorithm is the FISTA or ADMF. Okay. PM3D or CNN denisers using. Here for this plug and play regularization, proximal algorithm FISTA ADMF. Each iterate of the resulting PnP algorithm, that is this algorithm, each iteration involves some kind of inversion of the forward model. Involves some kind of inversion of the forward model, followed by deniser included regularization. Each iteration of resulting PnP algorithm involves some kind of inversion of the forward model. Here what the inversion of the forward model. Inversion forward model followed by deniser included followed by deniser induced regularization. A natural question in this record is that of optimality, namely do the PnP iterations what here doing, minimize some f plus g, minimize f plus g. This algorithm, this PnP algorithm here doing that f plus g. F means where f is a loss function associated with the forward model. That is this one associated with the forward model, and G is regularizer. G is the regularizer. This has straightforward solution if the deniser can be expressed as a proximal map. Straightforward solution if the deniser can be expressed in proximal map, as was shown to be the case for a classical linear symmetric deniser. Classical class of linear symmetric denisers However, this result excluded kernel denoises. Kernel denoises here excluded, such as non-local means that inherently non-symmetric. In this paper, we prove that a broader class of linear denoisers, including symmetric denoisers and kernel denoisers. Symmetric denoisers and kernel denoisers can be expressed as a proximal map of some convex regularizers G. An algorithmic implication of this result for non-symmetric denoisers is that it necessitates appropriate modifications in the PnP updates to ensure convergence to a minimum of f plus g. Apart from the convergence guarantee, the modified PnP algorithm are shown produced good restorations. Apart from the convergence guarantee, convergence with f plus g, the modified PnP algorithms are shown produced good restorations. In this paper, they have used 8 test image other than those in the set 12 data set that make up our 20 image data set. Okay, this figure area. This is the bridge. This is the car, clock, gold hill, lake, mantle, tree. Okay. Here, ground truth, that is example of image in painting for the pepper image. Example of image in painting for the pepper's image. C and D. Restored images obtained using scaled PnP, ADMM, SPnP, ADMM and the standard PnP, ADMM respectively. Rho equal to 1 in both cases. The respective BSNR with respect to the ground truth image are 29.04 dB and 27.94 dB, where E plot the objective values f of xk plus g of zk versus k of f, plots of the residual values on a log scale, log plots of the residual values on a log scale, log double vertical bar of xk comma zk 2 versus k. Here, example of image in painting for the pepper's image. For the pepper image, C and D image obtained using scaled PnP, ADMM, SPnP, ADMM and standard PnP, ADMM respectively. Standard PDMM respectively. Rho equal to 1 for both cases. Rho equal to here also 1, here also 1. The respective BSNR with respect to ground truth image or ground truth image BSNR value 29.04 dB and 27.98 dB. 27. Ground the BSNR value respect to ground truth are their ground truth image are 29.04 here and 27.98. Okay. And then plots for the objective values E plots for this one. Here E this one. Plots of the objective. Plots of the objective. Plots of the objective values. Values. F of xk. F of xk plus g of zk versus k versus k. Uh, this one also this figure plots of the residual values on log scale. Log scale x double vertical bar of s comma sk minus zk to versus k. Here this is for s PnP ADMO. This is for PnP ADMO. PnP ADMO. Here scale 0, 0, 20, 40, 60, 80, 100, 150, 200, 250, 300, 350, 400. F of xk plus g of zk. Okay. Here log of double vertical bar 0, 20, 40, 60, 80, 100, minus 8, minus 6, minus 4, minus 2, 0, 2. See here, yes, PnP, ADM, this color, this blue. PnP, ADM, this color, orange color. So, plots of the objective, so here, plots of the residual values on a log scale, residual log scale, yes, double bar of xk minus zk 2. Image in painting average BSNRs in dB of scaled standard PNB ADMM across 20 images. 20 images. Sigma uh, image impeding average PSR dB of scale standard PnP DMM across 20 images. Sigma omega m slash n. This is 10, 20, 30 sigma omega. These all are m slash n. Sorry, 10 by 255, 25 255, 30 by 255 all are sigma omega. This is m divided by n, 0.3, 0.5, 0.7. These all are m, these are n. So this is all are in BSNR, average BSNR team. In across PNB ADMM in 20 images. This is the for m by n. This is the BSNR value. Here, restored images using 3 PnP methods. Restored images using 3 PnP methods. This one scaled PnP ADMM using NLM denoiser. Same as figure 2C. Standard PnP ADMM here with TV noiser. Standard PnP ADMM with DNCNN noiser. This one. The BSNRs are 29.04 dB, 27.8